Hello everyone. Today I will present our work, Procedural Mistake Detection via Action Effect Modeling. In this work, we study how to detect mistakes in procedural videos by modeling not only how an action is performed, but also what effect it produces. Mistakes are common in real procedural tasks, such as cooking, assembly, and daily assistance. As shown here, errors often lead to undesirable outcomes, like spilling objects or knocking over tools. These examples highlight that procedural mistakes are universal and can happen even in simple activities. Mistake detection is an essential first step toward intelligent assistance. In the broader pipeline, it comes before mistake explanation and mistake correction. So in this work, we focus on identifying when and where a deviation happens, which is the foundation for future assistive systems. Existing methods mainly determine mistakes from the execution process itself. They focus on motion patterns or action representations, but often ignore whether the final outcome is actually correct. However, in many cases, the execution may look reasonable while the resulting object state or spatial arrangement is wrong. That is the core limitation we want to address. Our solution is Action Effect Modeling, or AEM. The key idea is to explicitly model the effect of an action so the detector can reason about both execution and outcome. This gives the model access to cues like object state changes and spatial relations, which are often crucial for recognizing subtle mistakes. We formulate mistake detection as a marginalization problem over latent action effects. Previous methods predict mistakes directly from the input segment feature. In contrast, our formulation decomposes the problem into three parts: effect frame sampling, effect-aware learning, and mistake detection. This gives us a structured way to connect action execution with the outcome it produces. This slide shows the overall AEM framework. First, during training, we sample an effect frame that best reflects the action outcome. Then we extract multimodal knowledge from that frame using both grounded visual cues and symbolic scene graphs. Finally, we learn an effect-aware representation and fuse it back into the action feature for mistake detection. Importantly, the expensive multimodal knowledge extraction is only used during training, while inference remains efficient. The first step is effect frame sampling. We want to find the frame within an action segment that best captures the resulting outcome. To do this, we rank candidate frames using two criteria: semantic relevance to the expected post-action state and visual quality. The top-ranked frame is selected as the effect frame. Next, we extract action effect features from two perspectives: object state and spatial relationship. In the visual branch, we use grounding DINO to detect relevant objects and encode their appearance and locations. In the textual branch, we use GPT-4o to generate a scene graph, which provides symbolic object attributes and relations. We then align the visual and textual features with a contrastive objective, so both modalities capture the same underlying effect semantics. In the third step, we introduce a learnable effect token, or EFT token, into the segment feature sequence. During training, this token is aligned with the extracted multimodal effect features through state and relation projectors. After that, the projected token is fused back into the original segment representation. In this way, the model learns compact effect-aware features without requiring external large models at test time. We evaluate our method on two egocentric procedural mistake detection benchmarks, eGOPR and Captain Cook 4D. On eGOPR, our method achieves the best overall AUC and EDA compared with prior baselines. On Captain Cook 4D, we also achieve the best precision and AUC. These results show that modeling action effects provides a clear advantage for mistake detection. This slide shows example predictions on real videos. In both cases, the model correctly assigns high mistake probability to the error segments, including knocking over the dripper and placing the tortilla on the table instead of the cutting board. These examples illustrate that the model can localize meaningful mistakes in time. Here we further compare behavior with and without effect modeling. The first several examples show that effect-aware modeling is especially useful for mistakes that appear in the final outcomes, such as wrong placement, wrong shape, or spilled objects. At the same time, the last example shows that the model can still detect execution errors during the action process. This highlights the complementarity between effect modeling and execution modeling. There are several directions for future work. First, we want to extend this framework from single-step effects to spatial temporal action effect modeling across longer procedures. Second, we want to move beyond mistake detection toward mistake explanation and correction. Third, we are interested in generalizing this idea to other domains, such as robotics. Thank you for listening. I would be happy to discuss any questions.